Hey, what's up, guys? This is Sheng here. So today, let's take a look at today's daily challenge problem, number 81, search in rotated sorted array number 2. So actually, this one is like an extension of the search in rotated sorted array number 1. Basically, the only difference is for this one is the it allows a duplicate numbers. But let's try to refresh our memories about how can we solve it without duplicate numbers. And so you're given like a sorted array which is rotated at some pivot point unknown to you beforehand, and it asks you to find the target. Okay, so if we have a sorted array here, let's say we have a 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if it's being rotated somewhere here, for example, if instead of that we have 7, 8, 1, 2, 3, 4, 5, 6, right? Let's say we have this example here, right? And still we need to use a binary search. But to search this one, we have to so the idea for this kind of rotated like array here, I mean, the first option is we can simply find the pivot point, right? I mean that's similar like to finding a mountain, right? So we can do another two binary search on those two sides. Let's say we find like the pivot point at this location, we can simply do a two binary search. First one, search from 1 to 7, and then search from 8 to 9, right? But the time complexity for that is we're gonna have like what to find the pivot point is gonna take us O(n) time to find it, and then we have we have to like log n search, right? That's definitely one options, and the other option is we can definitely just apply the binary search directly. But to do that is we're gonna need to check some few more conditions. So every time when we have a middle point, you know, since the array is different, since the array could be rotated, so the first thing we need to do is that we have to check from this middle point, middle point, which side is sorted, right? And for example, like let's say we're looking for 5 in this case, right? Let's say we're looking for 5, and then the middle point is 1, 2, 3, 4. I think it's somewhere here, right? That's the middle point. And once we're at this middle point here, we just need to check which part is sorted. So how can we check which part is sorted, right? I mean, we can either compare with the right pointer, or we can compare with the left pointer. So let's say, for example, right now this is the left, this is right, right? Let's say we use the left pointer to check which part is sorted, and we compare this middle pointer with the left pointer. So remember, it's a left pointer. It's not the first numbers because we're trying to sort the current left to right, right? If the current one is greater, it's either equal or greater than the left pointer numbers, and then we know okay the left side is sorted. Otherwise, the right side is sorted, right? And then once we have a sorted parts, we'll just um, and then we'll try to search in that part basically, if the target is within this sorted range here, right? And then we know we can simply follow the binary search rules to just for example this one, right? We know okay, so the right side is sorted, and then we'll just go to the we'll go to the right side, and then we see okay 5 is right, is in between this sorted the right sections here, so we can simply move our pointer to the middle plus one, the left pointer to the middle plus one. Else we just need to go to the left side, right? For example, if we instead of searching 5 here, let's say we're searching 8, right? Let's say we're searching 8 here, you know. So even though the right side is sorted, but 8 is not in that range, so that's why we have to go to the left point, the left side. So same thing for for the left part to be sorted. Okay. All right. So let me try to implement these things here. You know, maybe I'll try to explain a bit more there. So we have numbers there, like I said. So we start from 0, right, and then right equals to n minus 1, right? So template is very similar. Right, while left is equal or smaller than the left pointer, right? Then we have middle equals to left plus right minus left divided by 2, right? So the best case scenario is if the number middle is equal to the target, right? Then we simply return true, right? So now we check, okay, if the nums of left pointer is equal or smaller than the middle kernel's the middle one. So we need to do a equals check here because you know the left and middle could be the same, right? Could be the same numbers. Right, so here like the left side it's sorted, right? And then if the left side is sorted, then we can have a simple check here. Basically, you know, if the numbers of left is equal smaller than the target and within the range of within the range of this sorted array, then we know okay, we can safely put update the right pointer to the middle minus 1, right? Else it's not there, then it has to be on the other side, right? Which is the left equals to middle plus 1. So we're doing this like less or equal to the left, but only less to the right side because for the middle point we have already checked that. I mean, if the target equals to middle, we'll simply return. So there's no need to check the equal sign here, right? So that's that, you know. And else, right? Else is like the similar thing, right? So else is the right side is sorted, right? So basically, we just use this sorted to help us to fix one scenario, and then the else, of course, is the other scenario because this one. Okay, so similar thing, right? So for the right side, and if the nums of middle, right, is smaller than the target, then the nums of right, sorry, this equal sign, right? Then we know, okay, left is going to be middle plus 1, and also going to be a right dot middle minus 1. So the reason we are doing this is because, you know, because we know the rules for sorted. How do we move this pointer in a sorted array? That's why for this kind of like complicated cases here, we're going to transform it into a case that we know how to solve it, and then we just use that as a base case, which is we find the the sorted parts, and then within the sorted parts, we know that if the target is within that sorted parts, and then we can tell we know it's safely to just update the right pointer or the left pointer. And for the other case, we simply do update the other half. Okay, and that's that. So in the end, we simply return return false, right? If none of the, if we never find a match. Okay. Yeah, okay. Sorry about repeating myself. I think I just want to emphasize this condition here because the only when we find assorted parts, then we can use this range check here, right? Because if this part is not sorted, we simply cannot do a range check, right? We can only be sure to do a range check here. When this part, when the left to middle is sorted, then we know if target is within this range, then we know it has to be in that range, right? And then if it's not there, then it has to be on the other side. We basically repeatedly doing this kind of stuff for the same, for the left sorted array and for the right sorted array. Cool. So this thing, it will work for the case where there's no duplicate numbers. But for this problem, for this question, there is a like special case, right? So it allows duplicate numbers. But for the duplicate numbers, we'll have an issue here. So why is that? Let's say we have a 1, 3, 1, 1, 1. Let's say that's the case, and the middle point is 1, right? As you guys can see here, if we just follow the same logic here, so the middle point is 1, and we see, okay, so 1 is smaller, equal smaller than the left part, right? Then it will assuming, okay, so this part is sorted. It will just follow that sorted logic. It's going to be follow the assuming this is sorted array, and it will try to find the target within that range. But the truth is it is not a sorted, right? Because we have 1, 3, and 1. So that that's the issue we need to fix here. And so the easiest way to fix it is just it's like this, right? I mean, before doing this kind of check here, we just need to move we just need to move either the left pointer or the right pointer to a place that is not equal to the middle point. Then we can convert this problem to a non-duplicated number problem, right? Something like this. So while left is smaller than the middle, right? And what and the nums left is equal to the nums of middle. Then we simply move this left to the right until the left is not the same as the middle. Then we can safely apply this part. Okay. And same thing for the right side, right? While middle, right, is smaller than the right, and nums right is same as the nums middle, right? We also try to shrink that right side. So after these two steps here, right? So both the left side and right side, they're not we don't have a duplicate in terms of the middle, left, and right point. Then continue we can continue applying our our binary search here. Yeah. So what's going to be the time complexity for this one, right? I mean, for the non-duplicate number case, of course, it's a log n, right? It's a log n. But for if with the duplicate numbers here, the worst case scenario is what? Everything is the same. Everything is the same numbers. So what does it mean? It means that we have to go through everything. We have to loop through all the numbers to decrease the left and right one by one. So which means the worst case scenario for this search algorithm is going to be O of n. But on average, it should also still be log n. Yeah, cool. Yeah, I think that's it for this problem. And thank you so much for you guys to watch this video and stay tuned. I'll be seeing you guys soon. Bye bye.